Good morning. Our next unit is going to be covering solids and liquids, intermolecular forces, and thermochemistry. In this unit, you should be able to evaluate and communicate information about how to refine the design of a chemical system by applying engineering principles to manipulate the factors that affect a chemical reaction, and obtain, evaluate, and communicate information about the kinetic molecular theory to model atomic and molecular motion in chemical and physical processes. From our last unit, when we were discussing gases, we hopefully remember that gases have a low density, they are highly compressible, and can fill a container. Solids have a high density, are slightly compressible, and are rigid, and some properties of liquid lie in between those of solids and gases. You hopefully remember from our kinetic theory conversation that the solids have a definite shape and a definite volume. The liquids have a definite volume but an indefinite shape, so they will take the shape of their container, and the gases have an indefinite shape and an indefinite volume. The reason why each of those changes is occurring is because they have additional energy that has been inputted into the system, and that allows those particles to be able to move more freely as they go from the solid to the liquid, the gaseous state. One of the important aspects when we're describing solids, liquids, and gases is the role that energy plays in the transition between these different states of matter. When you look at these different phase changes, again, that is your change in state, so you'll see that termed as a phase change. There is always a certain amount of energy that is related to that phase change process. These processes are always going to be physical changes, which means for us that they are reversible. So that means that they can go in either direction. So if we look at water as an example, I could have water as a liquid undergoing a process where we will say add extra heat. Remember, the triangle represents the addition of heat, and that will form H2O as a gas. But in the same concept, we can take the gas and we can remove heat, and that would make the gas condense back down into a liquid. So it is a reversible process. We define that reversible process by using the double arrows. So this is the first time that you're seeing that. Whenever you see that you have the double arrows, that basically means that you have that reversible process, but it also will represent the fact that we can have an equilibrium reaction, and so, or process. When we talk about the equilibrium, it just means that the rate of the forward and the rate of the reverse processes are the same. So the rate of the forward process equals the rate of the reverse. This is going to become a very important concept throughout this unit and into the next few units when we talk about different equilibrium systems. During the phase change, when a substance is undergoing those changes in state, say from a solid to a liquid or from a liquid to a gas, the molecules are going to remain intact. The change in states are due to the changes in forces among the molecules or between the molecules rather than within the molecules. So one of the most common things that I hear about all the time, if I just have a pot of boiling water or a beaker of boiling water sitting on a hot plate and I ask what's the gas that's coming off, I'll hear a lot of kids say hydrogen gas or oxygen gas instead of just saying that it's water vapor that's being formed. Very common misconception with that. So just understand when we talk about this concept of the molecules remaining intact, hopefully you remember from our beginning units when we talked about physical changes that the identity of the substance is not changing. So this just means that the identity stays the same. The identity is the same, but we're just changing what state of matter it's in. So when we talk about these forces among the molecules or between the molecules, we term these as intermolecular forces of attraction. So depending on how strong those molecules are attracted to each other, and there's a lot of different factors that go into that we will discuss, but one of the big ones that we will be looking at are polarities. So as I warned you guys in class, You'll see a lot of Lewis structures with this unit as well. So we have to look at the type of bonding that's taking place between these different atoms to give us the polarities of the molecules. That will give us a lot of information about the forces of attraction that are occurring between the molecules. So you have intermolecular forces that are between. When we talk about the actual forces within the molecules, this is actually talking about what we call an intramolecular force, and that's essentially the bonds between the atoms. So we're now going to break down the different phase changes in terms of their energy situations. So these first few phase changes that we're talking about, these are all endothermic processes. So if you remember, endothermic means that we are absorbing energy. So the energy content is going to be increasing. So you can think about it in terms of the different states of matter and your knowledge of those states of matter in comparison to each other. So if ever I'm going from a lower energy state of matter to a higher energy state of matter, then it's an endothermic process. When we have the release of energy, and I know this makes it seem weird, but we have to kind of think about system versus surroundings with all this. But if I'm going from a higher energy state of matter to a lower energy state of matter, then energy is being released, and you'll see less energetic particles in that sample. So when we talk about a solid to a liquid, hopefully you remember that is a process that we call melting. When I have the liquid to a gas, that is a process that we call boiling, vaporization, or evaporation. And it does have quite a few different terms for it, and that's dependent on a couple of different factors dealing with temperatures and pressures. So we'll get into some of those different vocabulary terms a little bit later. But as we look at the solid to the gas, that is called sublimation. So again, you would skip the liquid state entirely. So when we're talking about the solid to the liquid transition, as we add energy to the solid, the motion of the molecules will begin to increase. If you remember, the solids just vibrate back and forth in place. But as we increase the energy, eventually those particles have violent enough vibrational movements where they can break free of those forces of attraction that are holding them together. And they eventually achieve a greater amount of movement, and we can have something that we call a disorder, which is a measure of entropy that would be characteristic of the liquid. So the disorder just means that they have more places that they can move around within the sample size. When we talk about the liquid to the gas, same type of concept. We have more energy being added. Eventually, some of those gas particles will form as the liquid molecules have enough energy to escape all those forces of attraction holding them together in the surface of the liquid. So eventually, I would have a larger amount of gas particles formed as the temperature continues to increase. And finally, when we look at the solid to the gas, this one is kind of unique. So in addition to having a proper amount of energy, we also have to look at the atmospheric pressure. We're going to talk about phase changes in terms of some different types of diagrams coming up here, and we will discuss this sublimation process in much greater depth at that time. When we go in the reverse processes, we have things like the liquid to the solid. So if we go liquid to the solid, that would be represented as freezing, and the exact opposite is taking place. So for all of the higher energy to lower energy states, these become exothermic instead. And so we're going to lose energy. The molecule's motion will decrease, and then eventually those forces of attraction are going to take over and will basically lock those solid particles in place together. When we talk about the gas to the liquid, if I go gas to liquid, that is a process that we call condensation. So we talked about condensation a little bit when we were discussing real versus ideal gases. And then in that situation, again, the temperature is lowered, so the gas particles are moving at a slower speed. their volumes would condense down, shrink a little bit, and eventually those forces of attraction will be great enough to lock those particles together and form larger droplets, and then they would fall out as the liquid. And then finally, the opposite of sublimation, going from a gas directly to a solid. If you go outside right now, since we're in February, you may have seen some forming on your cars or on your grass as an example of deposition, and that would be something like frost. So if you go out to your car and you see frost on the windows right now, that's deposition. So there's not enough moisture in the atmosphere to make it rain, but when it does finally reach that saturation point in the atmosphere, the temperature is too cold to have the liquid state, and so it just goes immediately from the vapor down to the solid. So here's where we're going to begin our work with the math portion of this, relating the actual amounts of energy to these different changes in state or heating or cooling of these different states of matter. So basically we have 5 different regions of space that we can see within this graph. So every time that we see a change in the direction of the line, that is changing one of the processes. So if you think logically, at the coldest temperature, that's where we're going to have a solid. So you can see down here, I have ice, but if it's not water, this first line here would represent the solid state. And then this part here, the horizontal line, that is dealing with our phase change. So when we are discussing our phase change again between the solid state and the liquid state, that would be an equilibrium between melting and freezing. So I have a combination in terms of the materials inside. I have both the solid and the liquid that are present within that mix until it gets heated up enough at this point where you can start to see the increase. And so now between 0 and 100, I hope that would make sense. This whole entire phase right here would be our liquid state. And then we get up here to 100 degrees, and hopefully you know the significance of water at 100. That's where it starts to boil. So at this point here, I now have a second phase change, and I have an equilibrium now between the liquid and the gaseous states. So that will be where I will have the boiling and condensation taking place. And it's going to stay at 100 degrees until all the water has been boiled, and at that point then the steam can increase its temperature. So that last diagonal line, that's where I would have the gaseous state. So just a couple of things here. When you see that horizontal line, again, that is representing a phase change. And then when you see that vertical line or that diagonal line, that is representing just a particular state of matter. So again, whether it's solid, liquid, or gas depends on where we are, but they will always have a diagonal when we're just heating up the substance. The key thing to remember, phase changes, they are occurring at a constant temperature until all of the particles have been converted from one thing into another. So again, you have this basic shape for any of your graphs. We'll get back into it a little bit later here, where we actually focus on the actual amounts of the energy that are required to make these conversions take place. So now when we're talking about those different phase changes and the energy that's involved in them, we call these the molar heat of fusion, which is the energy required to melt 1 mole of a substance. So again, when we're talking about the melting process, I'm just going to come down here. When we're talking about the melting process, because that is an endothermic process, the energy is going to be a positive change. And then if we are freezing, because it's going from the liquid to the solid state, we have to get rid of energy, and so that's going to be a negative amount of energy. However, the amount of energy itself stays the same. So the energy required to melt or freeze 1 mole of a substance, called that molar heat of fusion. And then we have that molar heat of vaporization, which is the energy required to change 1 mole of a liquid to its vapor. So again, same type of concept. We're talking about boiling and condensation for this, and if we are boiling, we're adding that amount of energy, because again, higher energy state of matter as a result. So we're adding in the energy, and then if it's condensation, we're removing energy. So I would be having a lower energy content overall. So just remember the sign for the energy. Its only significance is showing the direction of heat flow. Okay, so again, if the sign is negative, then that means that energy is released. So the final substance will be lower in energy. And if I have a positive change, that means that energy is absorbed. And so the final substance will have an increase, an increase in energy. So again, that is lower in energy as a result. Okay, so again, we have lower and higher in energy. Sorry, I was trying to read my handwriting there to see what that was. So again, higher in energy for the energy being absorbed, lower in energy for energy that's being released. Okay, so let's do a practice problem here. So it says that the unusually high value of the molar heat of vaporization of water, 40.6 kilojoules per mole, is an important factor in moderating the temperature of the Earth's surface, and it results in an enormous transfer of energy to the atmosphere as liquid water evaporates as part of the hydrologic cycle. Calculate the amount of heat in kilojoules needed to evaporate 10.5 kilograms of liquid water at 100 degrees Celsius. So in order to solve this problem, notice my unit, I have 40.6 kilojoules per mole, and I'm starting with 10.5 kilograms of liquid water. So I need to convert my kilograms into moles. So if you remember from our metric units, when I start with that many kilograms of water, 1 kilogram of water is the equivalent of 1,000 grams. And then the molar mass of water is 18.02 grams. So 18.02 grams found in 1 mole. And I solve for that, and that will be 582.7 for my number of moles. And then I know here, from an energy calculation standpoint, I have 40.6 kilojoules for every 1 mole. So if I multiply that times the 582.7 moles, again, my moles cancel, and I'm left with kilojoules, and that gives me 23,657 kilojoules. So again, putting that into scientific notation, I can have 1, 2, 3, 4, so 2.37 times 10 to the 4th kilojoules. So my correct answer would be C. All right, so now we're going to focus on some of the properties for solids and liquids. We've already talked about properties of gases in our previous unit, so now we're going to focus on solids and liquids. So to start off with, we have crystalline solids, and these are substances with a regular arrangement of their components in the form of a crystalline solid. So you will hopefully remember a term that we discussed back in our bonding unit, which was a crystal lattice. So when we have ionic compounds, they can form a crystal lattice where we have that alternation of the oppositely charged ions within the system. You can see here with this picture, if we focus on just one of these different ions here that are trapped in the center of that crystal, I would have 1, 2, 3, 4, 5, 6 different oppositely charged ions that are attracted to each sodium within that crystal structure. And so as a result, in order to melt this compound, we have to break each of those 6 bonds between those different ions. And so that's why the ionic compounds have such very large melting points and boiling points, because it takes so much energy to break apart all those interactions. We talked about with our periodic trends unit, we talked a little bit about how we can look at the charges of the compound. The higher the charges are, the greater the melting points are going to be because of Coulomb's law with that force of attraction. Your Q's will be higher, having a positive and a negative versus a positive 3 and a negative 3. There's going to be a stronger force of attraction with the +3 and the -3 as a result. So we have very high melting points, boiling points, very brittle structures for those crystalline solids. We can break down the crystalline solids into 3 types. When we look at ionic solids, again, the ions at the points of the lattice that describe the structure of the solid. So again, you saw that with that diagram on the last page. So you have to break apart all of those different bonds between the ions to get them to break apart. Then we have molecular solids, and these are going to be covalently bonded molecules that are at each of the lattice points. So big, huge difference here. For these molecular solids, these will not be bonded together. So the molecules are held together by those intermolecular forces, which we can abbreviate as IMFs moving forward. And so as a result, again, these are between the molecules, not within the molecules. And so that force of attraction is much weaker. So again, between the molecules, so much weaker. So your molecular solids typically will have much lower melting points or boiling points because you're only breaking the interactions between the molecules, not the bonds within them. And then finally, we have atomic solids. You'll also see these termed as covalent network solids. And as we go through and look at some more examples, you'll see it as an atomic network solid. It works the same way, but basically you have a very similar structure to the ionic solids in the fact that a lot of the atoms are going to be bonded together. So the atoms held together by bonds. And so we have to break all of those interactions between those atoms by breaking the bonds. So much higher in energy as a result. So these two here, these will be high melting points or boiling points. The molecular solids, these will be lower melting points. So we'll talk about the different forces that affect these later on in one of our next videos. So again, I just wanted to give you a couple of examples to look at for some of these different types. So the first one that we have here would be an example of the atomic network solid, or that covalent network solid. Diamond is an example of that, hardest structure known to man. And you can see here, hopefully you remember this basic structure that we have. That is a tetrahedral structure, 109.5 degrees, sp3 hybridized for the different bond angles and the carbon atoms with each other. And so what you notice here is that that allows us to have a 3-dimensional array for the structure, and as a result it makes it much more difficult to break the bonds apart. We have 2-dimensional structures for some of these as well. Graphite where we have carbon just in a two-dimensional structure. It's in rings instead of in this really strong three-dimensional structure. It's also an atomic solid, but it's not as strong, and that's because the true bonding only occurs in 2 dimensions, and then it has weak intermolecular forces in that third dimension holding the different layers together. That's why graphite, if you put pressure on it, it will cleave off a layer, and that's why we use it for a writing utensil or for lubricating a lot of different machine parts, because it will easily slide off. You saw the ionic crystal, we talked about that already, and then here's an example of a molecular solid. If we look at ice, again, I have the individual water molecules as the discrete units. So you have the sticks in between the atoms that would represent the true bonds. All these little dots right here, that represents the IMFs that are acting in between the molecules, holding them together in place. So again, just to recap for your ionic solids, they are stable substances with very high melting points. The higher the melting point is for the solid, the stronger the forces of attraction between the ions. They're held together by those strong forces that exist because you have those oppositely charged ions, so you have that full-on magnetic force of attraction that are locking them together in place. So again, when we talk about the molecular solids, you can see a few more examples of this. Here we have the sulfur crystals. If you've ever seen sulfur, it's a yellow, it's brittle, it's very smelly, but they contain S8 molecules. And then we also have white phosphorus. There's another form of phosphorus that's called red phosphorus. But white phosphorus, you can see here, it is explosive with the oxygen in the air, so that's why it's being stored under the oil. If you remember, we had to do that with sodium metal as well to keep it from reacting with water or oxygen in the air. But the white phosphorus contains P4 molecules, and so again, they're going to be held together by those weak intermolecular forces between the different molecules. So the S8 is the base unit, and then it has the weak attractive forces to other S8 molecules. Melts at very low temperatures, and they're going to be held together again by weak intermolecular forces. And then when we look at the atomic solids, your fundamental particle is going to be an atom, but the properties are going to vary greatly. You have some that are found in group 8 that have very low melting points, and then you have others, such as the diamond, that are going to have very high melting points as a result. So it all depends on the nature of the bonds. Are they two-dimensional? Are they three-dimensional? To allow us to figure out the strength of these different atomic solids. So just like diamond came from carbon, you want to watch for silica-based compounds as well. So anything that has Si and O has the possibility to be an atomic or a covalent network solid. Let me put that down here over to the side. So you'd have a covalent network solid. And then you could also watch for some boron and oxygen compounds. Sometimes the boron is added into the silica. The silica basically a lot of times is glass, and so it has, instead of just being SiO2, it has SiO4 with a lot of different interconnections. So instead of having the same type of expectation that we would have for carbon dioxide, since silicon is directly below, has the same number of valence electrons, we would think it would be SiO2 as 2 double bonds, but what we end up seeing, this would be our expected, but what we would actually see would be something like this, where I'd have the Si, and it would be singly bonded to 4 different oxygens. These would then be bonded to other silicons, and you get a big repeating pattern. So again, you have to break apart all those different bonds between the oxygens and the silicons. That's why glass has a high melting point. We can add different things in to make some of those specialty types of glasses. So we have things like borosilicate, where we've added some boron into the silicon to change up the pattern and improve on some of its properties. But you can watch for boron and oxygen compounds and silicon and oxygen compounds, as well as the carbon for your covalent network solids. So as we now move on to our properties of liquids, we're going to begin with viscosity. Viscosity is a resistance of a liquid to flow. If you remember, the particles inside of the liquid, again, have the freedom of motion, so they are fluid. But because of the forces of attraction that are occurring between the liquids, the stronger the force of attraction, the greater the viscosity. So it's related to the ease at which the molecules can move past one another. And again, the viscosity is going to increase with stronger intermolecular forces and also decrease with higher temperatures. So again, if you think about that, if we increase the temperature, again, just thinking about that increase in temperature, that means that we're going to be adding extra energy. So they have more energy to overcome those forces that are trying to hold them together. You can think about syrup. If you go to, I don't know, Cracker Barrel or something like that, should get them to do a paid promotion for that. You go to Cracker Barrel, they bring out like a hot thing of syrup with you if you order pancakes, and it will flow out of the bottle very easily. If you took that bottle home, stuck it in the refrigerator, and then you try to pour it out, it would come out very slowly. So for the older people like myself, we always used to hear an expression, especially from like our grandparents, if we were not doing something fast enough, they'd always say, oh, you're moving as slow as molasses in January. If you think about the temperature in January, it's normally pretty cold. So syrup, molasses, would move very slowly as a result. When we're talking about viscosities in terms of the same types of liquids, where we look at something like organic molecules, as you can see here, hexane, heptane, octane, nonane, decane, the greater the molecular formula is for the molar mass is for that compound, you're going to have an increase in velocity. So higher the molar mass, higher the viscosity will be. So just something you can look at there. And then we'll talk a little bit about the straight chain versus the branched compounds. Again, the straight chains, because they can just kind of sit on top of one another, kind of like what you're seeing here in the little diagram. If you think about that as being like a straight chain molecule, you have more area of contact, more surface area between the molecules, and so you're going to have a greater force of attraction. So when they have all these straight chain molecules, they can just kind of pack one on top of another and make it very well organized, and so you get a lot of interaction between them. Whereas if I had something like this, where I have an increase in the number of molecules, but you can kind of see here, if I just kind of draw a circle around to show the radius of the molecule, you can see there's very little interaction or space in between the molecules. So the more branched it is, the lower the viscosity will be, because there's less force of attraction acting on them. The next thing that we have is surface tension, and surface tension results from the net inward force experienced by the molecules on the surface of the liquid. So you can kind of see here in the diagram down below, on the surface it has forces pulling it in a diagonal direction going down, and in the horizontal direction going across the top of the surface. So I don't have anything pulling in the upward direction. So there's a net force that's pulling to the side and down when I look at the top molecule. If I look at the molecule underneath the surface, now I have equal and opposite forces taking place in each direction. So I have a balanced force underneath, where I have an unbalanced force on the surface. And so as a result, any molecule that's on the surface, since there's no upward force to cancel out that downward force, the surface of the molecule is going to feel a net pull going in the downward direction. And so it's going to bubble up on the top. So when you see those liquids bead up, that's due to surface tension. And so the stronger those forces of attraction, the more those particles are going to bead up. So if I spill certain types of liquids, if it's a nonpolar liquid, you're not going to get that beading action. They're just going to spread further across the surface of the table or the floor, versus something like mercury, one of our liquid metals, or water. You find that those things can bead up more frequently because they have stronger forces of attraction. So you had the experiment that you guys probably did. If we get back in the classroom here soon, we'll do this as well, where you do the little drops on the penny to see how many droplets you can get on the surface of the penny before it spills over. So that's a consequence of surface tension. If you guys want to, you can try this out at home pretty easily. Just find a paper clip and get like a bowl of water and see if you can get the paper clip to stand on the surface of the water. So that's a little activity that you guys can do here after you get done watching the video. The last property that we're going to look at is dealing with capillary action. So capillary action is the ability of a liquid to rise or fall in a glass tube or other container. This is due to the attractive forces that are occurring between the liquid itself and the glass or the plastic in the container. You can think about just a straw that you would get at Chick-fil-A, McDonald's, where a lot of people are just sitting there playing with their straw when they're talking, they're bored. But if you ever look, the water level or the level of the drink inside of the straw is always above the level of the liquid in the cup, and that's due to that narrow opening that allows it to rise up inside. So when we're describing those forces, we have a cohesive force, and those are the forces that hold the liquid particles together. And then we have the adhesive forces. So those are going to be the forces between the liquid and another surface. So when we talk about the capillary action rising, that is telling us that the adhesive forces between the container walls and the liquid are stronger than the attractive forces between the liquid particles. If the capillary falls, then that tells us that the cohesive forces are going to be greater than the adhesive forces. This is going to relate to the meniscus that we could see in a graduated cylinder. So if we look at a couple of examples of the meniscus or menisci, I guess maybe, for different liquids. If we look at water, and you can see that we have the dip going down inside of the container. That dip tells me that the adhesive forces are stronger because it's pulling the liquid up on the sides, attracting to the plastic or the glass that it's found in. Whereas when we look at mercury, now the mercury is going to be more of a dome shape or the convex type of shape instead of concave, because of the fact that it has stronger cohesive forces acting on the liquid particles compared to the adhesive forces between the glass and the mercury. So again, stronger cohesive forces, you're going to get that convex shape. If you have a concave shape, then that means that you have stronger adhesive forces taking place. So we're now going to begin to look at the relationship between the vapor pressure of a liquid and its boiling point that we will see. So first off, by definition, the vapor pressure is going to be the pressure that is created by the liquid particles that have enough energy to escape into the gaseous phase, and they are holding over the top of the liquid. So again, this has to be in a closed container to keep the particles in close proximity to the liquid. If it's an open container, they can just go and be released into the atmosphere, and they would never condense back down into the liquid. So when we look at this, at any temperature, some of the molecules in the liquid have enough energy to break free. That's that concept of evaporation. And hopefully you can think about the relationship as we increase the temperature, the vapor pressure will increase because we're going to have more evaporation taking place. So the fraction of the molecules will continue to increase at the higher temperature, we look at this curve underneath the in this diagram here. This is what we call a Maxwell-Boltzmann distribution curve. And for calculus, when you get to that point, you'll talk about integration for finding the area underneath the curve. The actual area underneath the curve is the same if you have the same number of particles. But in this case, because at the lower temperature, fewer of the molecules will have a different amount of kinetic energy. So that's why we have the larger peak occurring on that lower temperature. And so the little dotted line here, that's kind of like our threshold to see what is going to actually take place. So at the lower temperature, this small little fraction right here would have enough energy to escape into the gaseous phase. But at the higher temperature, notice the curve average is spreading out further to the right, which means that the average has a higher kinetic energy. And I have a larger portion of the molecules, the red plus the blue portion, that would now have enough energy to evaporate and escape into that gaseous phase. So from a pictorial standpoint, you guys can see here when I have a liquid inside of this little device here, as I open the valve and I pour some of the liquid into this evacuated flask. So again, there's no air particles inside, so it has zero pressure. I'm going to add the ethanol into the system, and now we're going to start to see the pressure increase as some of those particles begin to vaporize. And so I'm going to have a net effect of the liquid forming gas, but notice there's no gas coming back down to the liquid. At that point, when the system has reached equilibrium, which is what we call the equilibrium vapor pressure, the number of arrows, if you notice, going from the liquid into the gaseous phase is going to be identical to the number of arrows pointing from the gaseous phase back down into the liquid. So again, when we reach that equilibrium vapor pressure, that is what we would be looking at for the overall vapor pressure within the system. And then as more molecules escape into the gaseous phase, I'm going to have more particles making collisions, so that pressure would increase. We can relate this to our boiling point. I know most of the time we always think about the boiling point just being a finite number, but that's not actually true. The boiling point is dependent on the atmospheric pressure. So a true definition when we're talking about boiling points, that is going to be the temperature where the atmospheric pressure equals the vapor pressure, and that equilibrium vapor pressure. So from here on out, I'm just going to abbreviate the equilibrium vapor pressure as EVP, just for short. So when those two are equivalent to each other, that is when we have the boiling process take place. So it is very easy. Most people know if I just simply ask you what's the boiling point of water, the vast majority of people would tell me 100 degrees Celsius. Most people don't believe me though when I tell you that I can make water boil at 30 degrees Celsius, 40 degrees Celsius. And I can bring a vigorous boil within that system. And that's due to the changes in the atmospheric pressure. The vast majority of the world's population lives within 1,500 feet of sea level. And so we don't really see many big changes in the boiling temperature for water. But if you went to Colorado and you were up in Denver or in Pikes Peak or something like that, where you have altitudes greater than 5,000 feet, you would notice a large difference in the boiling point of water, which means that you'd have to cook your food for a longer amount of time because it's not supplying as much energy to the pasta or to the soup, whatever it is that you're making. So vapor pressure directly relates to the boiling point. Again, as you increase the temperature, you increase the vapor pressure. There's a chart that you could see for a particular liquid that would list the vapor pressures at a specific temperature. So now let's look at our relationship that we have between vapor pressures for different substances at the same temperature. So as a review, again, the boiling point of a liquid is the temperature at which its vapor pressure equals the atmospheric pressure. We have another new term that we can use, which is called a normal boiling point. And that normal boiling point is occurring the temperature where the vapor pressure is exactly equal to 1 atmosphere or any of its equivalents, 760 millimeters of mercury or torr, 101.325 kilopascals. But I want to talk about the different substances. So when we look at these things, we have a direct relationship. The strength of the IMFs, as those increase, you'll have an increase in the boiling point, which means that for any substances at the same temperature, the weaker substances will have a greater vapor pressure. And I hope that makes sense. This is always one of those very confusing concepts that people have, because if I have a substance with a higher vapor pressure, then that means that fewer of those liquid particles are being held together at the same temperature. So I have more particles that have had enough energy to overcome those forces of attraction between the liquid molecules, and they're allowed to escape into the vapor phase. So these are going to be inversely proportional. The stronger the IMF, the lower the vapor pressure of the substance. We're now going to begin to look at the phase diagrams, which are going to be displaying the state of a substance at various pressures and temperatures, and the places where equilibria exist between phases. If you remember that first phase diagram that we looked at, it was just simply looking at temperature versus the amount of heat that is being added. So it neglected this concept of pressure. So this diagram gives us a little bit more information. You'll notice that I have pressure found on the y-axis versus temperature on the x-axis. All the different lines that we see here with the boundary between the different colors, these are going to be the areas where we have that equilibrium taking place. So again, that would be where we would see the phase changes at a specific temperature and pressure. So you can see I have the solid further over to the left, and I hope that makes sense, because at lowest temperatures I should have the solid, and then I have the liquid in the middle, and I have the gas down on the bottom. This is the phase diagram for carbon dioxide. Anytime that you see a positive slope for the line between the solid and the liquid, so positive slope, just a little interesting fact, that tells us that the density of the solid is greater than the liquid. Now, when we look at the diagram, we have the triple point here, which is a very interesting concept. That is where all three states of matter are found in equilibrium with each other. So if I had a sample of matter that was found at equilibrium, which we're going to actually do in the lab in a couple of days, you would actually be able to see the solid particles, you'd see the liquid, and you could see the gas bubbling inside of the container. Very rare to actually see that take place. But now I wanted to address simply the sublimation and deposition that we were talking about before. So what basically takes place here with substances that will just sublime or deposit with skipping the liquid phase of melting and freezing, basically what is going to take place there is that we have to look at where the atmospheric pressure lies. And so typically what you would find is that the atmospheric pressure, 1 atmosphere or its equivalent, lies below the minimum temperature or pressure that is required to have the liquid state. So this is the minimum pressure for the liquid. I guess I should switch that over to a different color now since it's on that white background. So this would be representing the minimum pressure to form the liquid. And since the atmospheric pressure is lower than that minimum pressure for the liquid, it goes straight from the solid into the gaseous phase. So you can see that the liquid vapor interface, or the phase change between the liquid and the gaseous states, are going to start at our triple point right over here, and then it is this red line between T and C where we have the critical point above which the liquid and the vapor are indistinguishable from each other. So we have what we call a supercritical fluid at that point. So you have a certain temperature where you would not have the liquid state existing above that, or the gaseous state existing above that. It'd be a mix of the two. So when we look at the solid and the liquid line, that would be the blue starting at T and going up, and then finally for solid and gaseous boundary, that would be T all the way down to the origin, where we have that green line, and that would represent the phase change between the solid and the gaseous state directly. So we have a critical point, you'll see a critical temperature and a critical pressure. The critical pressure is the temperature above which the gaseous state cannot exist any longer. It would be as that supercritical fluid, which would be more of a liquid than it would be a gas at that point. And that's just because the compression is so high that it would force those particles together so close to each other that eventually they're going to bind together no matter what the temperature is. So here's where we get into the significance of these phase diagrams. So as I was mentioning before, I can make water boil at 40 degrees if I change the pressure enough. So any point along these lines, starting at the T going up to C for the liquid to the vapor state, T up to the end of the blue line, I'll just put that down as like a D over here. Any point along that line, temperature and pressure, would cause the liquid to freeze or the solid to melt. And so same thing, T down to the origin here, that would be the line in between any point, temperature and pressure, where you could have the solid and liquid phase change, or solid and gaseous phase change taking place. So it's all dependent on pressure. So you can see as the pressure drops, the amount of temperature required to make that substance boil will get lower as you go. So you can see that with carbon dioxide, how it would look. For water, a little interesting for the phase diagram there. If we're dealing with the water diagram, you would actually see this come out. I'd have my triple point here, but you'd actually see the line go back and have a negative slope. That, again, as I was mentioning before, would represent the fact that the solid is less dense than the liquid, because it has that negative slope. And then it would come out and go over here. Now, you'd have your normal boiling point for water somewhere up here. So again, coming here, although water can deposit or sublime under certain conditions, or sublime or deposit, typically at our atmospheric pressure, this being 1 atmosphere, these would be like your normal melting and boiling points that we would see. So I'd have this being the 100 degrees Celsius. This could be the 0 degrees Celsius for the normal freezing point or melting point, and then you have the normal boiling point over here. So the diagram changes just a little bit due to where the atmospheric pressure happens to be. Again, for the carbon dioxide, this would be the 1 atmosphere of pressure down here. So all we would have would be the phase change between the solid and the gaseous state. So just to finish this up, as we look at something like carbon dioxide, again, getting a little bit closer to a true diagram for what we would see. With the carbon dioxide, you'll notice again that the liquid state cannot exist below 5.11 atmospheres. So with our normal atmospheric pressure, as I had mentioned on the previous slide, the temperature being somewhere around negative 78 degrees Celsius, 110 degrees below zero, we would just have that transition between the solid and the gaseous state. So that's why when you put a piece of dry ice onto the countertop, you just see the little gas being given off, or you put it into a beaker of water and you just see all the gas coming out for like all the fog effects that you would have. And that's because the liquid state doesn't exist at normal atmospheric pressure. But if you pressurize the container, then you have enough pressure to get up to the point where the liquid can exist. So again, above 5.1 atmospheres, you can actually get the liquid state to form for carbon dioxide. And that's what we're going to do in the lab coming up. So later on this week, you guys will actually get to see liquid carbon dioxide, which is a very rare thing on Earth. So that wraps up the solids and liquids portion of the video. We'll spend some time doing some practice problems with the heat conversions and do a lab on some of the phase change stuff coming up, and then we'll get into intermolecular forces next, and then after that we'll get into the main meat of our unit, which will be covering thermochemistry. So we'll deal with specific heat and enthalpy, entropy, and Gibbs free energy calculations. So have a great afternoon. Go ahead and try to work on some of the practice problems that are online on the Teams page for you, and come to class tomorrow with questions.